General relativity, step by step. I've got the Friedman equation here, and of course what I'm going to do is to rewrite a dot as dA by dt and solve and try and get some integration going. Okay, so what have we got? We've got that dt equals dA over h of t0 times, and it'll be a square root because this is a squared term here, and what have we got? We've got omega k plus the matter term over a plus the radiation term over a squared plus the vacuum energy v omega v times a squared, and it's a square root because we've got this squared there. Now what you want really is to have an analytical solution for this, but the analytical solution, well, it's only just integrable analytically. You've effectively got a fourth order polynomial here because you've got a positive +2 power and a -2 power there. So you've got a fourth order polynomial to deal with. And the whole thing is, well, I hesitate to say it's analytically soluble because it's so long, it's pages and pages of dense mathematical terminology that it's effectively not analytically soluble, and that doesn't really help. It doesn't really help to write it down in its analytic form because it's literally dozens and dozens of pages of complicated algebraical expressions. So what I'm going to do is I'm going to consider special cases. I'm going to consider special cases to help our understanding cases. And the first one I'm going to consider is the radiation-dominated universe. Radiation-dominated. If you look at this expression here, you can tell that if A is very, very small, then this term here will dominate, and you can neglect all the others. So radiation-dominated universe. So let's have a look at that. We've got dt equals dA over the Hubble constant now times the square root of omega r over this term here over a squared. Is that right? Yeah. Equals. Well, it's 1 over h of t0 root omega r times the integral of just a dA, isn't it? Because it's 1 over the square root of a squared. And that's the integral of dt. So taking this up on the other side, h of t0 root omega r times t equals a half a squared plus a constant. And of course we're going to set that constant equal to 0, I guess. Doesn't really matter. It's just all it's doing is affecting your offset of time. So that basically says that A equals, taking that 2 up there, the square root of 2 h of t0 square root of omega r times t with a suitably chosen